All right, guys, sorry I'm not here for this last Block Friday. So we're going to do a 3.3 sampling distributions as our last lesson in the unit, and not a bad one. So once you're done with taking notes on this video, again, anything using notes could be used for open note quiz. You guys can do like an activity which the sub can get you. So 3.3 sampling distributions, we're actually going to use like M&Ms as our example. So, it says fruit snack experiment. We're just going to change it to M&Ms, right? So let's say all of you guys have a bag of M&Ms, which obviously you don't, I'm not here. But do you think each bag of M&Ms has the same number of M&Ms, right? So if I gave you guys all like a full-size M&M bag, how many do you think you'd have in there? You think we'd all have the same or not? So, the likelihood is that we wouldn't all have the exact same number of M&Ms. It's just kind of like a machine that will put them in there. It might just be done by weight within a certain amount. So obviously, if you're the company, if you have too many M&Ms, if you overfill a bag of M&Ms, I guess it could break, but also you're giving away your product without people having to pay extra for it. So you don't want to have them overfilled. However, if you have too little in there, then people might complain, and then you'll hit social media for not having enough M&Ms in your bag. So you want to have a number set in mind, but you also don't want to pay somebody to individually count how many M&Ms are there. And so like you have what's called a tolerance level. Like you are okay with being in between certain values. So, if on average they're supposed to have, I don't know, like 30 of them, you might be okay with 34. You're not giving away too much of your product. You might be okay with like 27. You're not screwing people too much, but like you want to be within a certain range. So maybe a good tolerance would be like 4 or 5 M&Ms, where you could be over by 5 or under by 5, but as long as you're within 5, people aren't going to get upset. You're not giving away too much of your products. Like you're pretty close. But obviously, the closer you are to the same number over and over, the better. So with our experiment with the M&Ms, right, I was going to give everybody like a thing of M&Ms, so I'm really sorry. I'll make it up to you. How many M&Ms do you have? So we could say, like, for example, if we did a sampling distribution, right, let's just say, this could be like a frequency, one person, 2, 3, 4, 5 people, right? And let's just say like this is 0, well, maybe not 0. We're actually going to do a break here. We'll start with like 25 M&Ms, then like 26, 25 to 26 would be in here, 26 to 27 would be in here, 27 to 28 would be in here. So we got 25 to 26, 26 to 27, 27 to 28, 28 to 29, 29 to 30, and that's kind of like our ranges. So this is anything, like if you had 25, you can be between 25 and 26. You can kind of figure it out. So let's say I gave you guys all a bag of M&Ms. We had like, say we had 3 people that were at 25. Let's just say that's 25. We have 3. Let's say we had 2 people who were at 26 M&Ms. We had 2 people that were at 27 M&Ms, 1 person at 28 M&Ms, and then like 2, let's say we had, 2 people at 30. And then, so we had 2, 2, 1, 2. So, I mean, that's 10 of you guys. Maybe we had 1 person, let's say that this is my 24 M&Ms. We had 1 person here, and get to the 12 people. We had 1 person who had 31, right? 31. So like, let's say that would be our histogram of our sampling distribution, right? How many people had these number of M&Ms? So 1 person with 24, 3 people with 25, 2 people with 26, 2 people with 27, 1 person with 28. Oh, this should have been 29. This should have been 30. I'm off by 1, but whatever. You kind of get the idea, right? So what we're talking about when we do these sampling distributions, right? If you all had a bag of M&Ms, it's not a lot of people here. Might be 12, but we want to know, how does this relate to the population at large? So can our small sample of M&Ms reflect the size of all M&M bags, which would, like, of the same size, obviously, like a full size or whatever, at large, right? So does our small population or our small sample affect what it is for like all of the bags out there in the whole world of those same M&Ms, right? So if it does, we can use what's called statistical inference. So a little bit more definitions. You guys can pause this video as often as you need to get the definitions down. But statistical inference is basically you're taking your results from your sample and then you're applying it to the whole population. So that would, in our case, would be all of the M&M bags in the world that are the same size. Do our results that we got from our class of bag M&Ms, does that mirror the entire populations? If it does, you're using what's called statistical inference, right? You're taking your result and applying it to everything. Now, the numbers you're going to be using to like describe all these changes, right, in our statistics class. The parameter is when you describe the population. You can use it as a percentage, but sometimes it's just the average number. And so usually if it's like an M&M bag, it'll say on the back of it like, you know, serving size, and it could say like, maybe it's 28 M&Ms, right? So they think on average that that bag has 28 on average. So that would be like a parameter. The overall average for all the M&Ms would be 28, right? But the statistic might be the average, doesn't have to be percentage, doesn't have to be a percentage, but it could be like the average of the actual ones that we looked at. And if you had our values, right, from our thing, you know, we might have a smaller average. I'm not going to add all these up, but let's say that our average ended up being like a 28.2, right? Just to throw out a number. So that just means our class average of M&M bags might be a 28.2. That's our statistic, right? Because it's from a sample. We don't have a parameter in our example because we're not basing a parameter off a population. So a parameter is a number to describe the population. That's all of the bags. The statistic, that's what we found in our small sample, and that, like I said, that could be our average number of M&Ms, which let's say it's 28.2, and maybe on the side of an M&M bag it says 30, so the population's a little bit different. We got screwed out of a few M&Ms, but on average, but that's it. So again, in our study, the parameter would probably be, you know, we didn't do a full scale, we didn't do hundreds of thousands of M&M bags and sample them and see how many are in each. So we don't have a parameter, but we could maybe base it off of the nutrition facts. And if they think, you know, if they do it all and they have all the studies out there, it might be 30 M&Ms in a bag on average. But our statistic had it just from our sample, statistics based off a sample. They both begin with S, easy way to remember it. Our statistic may not be exactly the same as the parameter, which means we really probably shouldn't use statistical inference because our results are not the same as the parameter's results. Our statistic is different from the parameter, which just means that our sample size was probably too small, right? And that kind of answers this question. So can we be confident that our statistic, like our average of 28.2, which I didn't even calculate, of tolerance, I didn't even do the tolerance, I just said our statistic for average number, but we could say the tolerance, you know, might be like 1.2 or 1.8 if the average is supposed to be 30 and ours is 28.2, we're off by 1.8. But basically what I'm trying to say is, can we be confident that that would be mirrored as a parameter for the entire population? Which means, can our average number of Skittles, right, is that reflected in the overall average of all the Skittles? So you might say yes, like, and be like, well, if you look at our data, you know, we're all around 30. They're pretty close. It's not like we had any that were way off that totally threw the data off. You could say yes, but probably more likely it's no, right? We got such a small sample size, which again, we just made it up. I didn't even give you guys the M&Ms, but this is such a small number of M&M bags that we really can't be confident that that's going to be the same as all of the M&M bags all over the world, right? So probably not. And that brings us to our last definition for today, which is variability, which is just the variability of a statistic is determined by the sampling distribution. Basically, in layman's terms, if you have a ton of things in your sample, like way more than just 12 bags of M&Ms, like 500 bags of M&Ms, the larger your sample, the less the variability, the smaller the variability. If you start repeating these these, you know, samples over and over and over and over, you're going to see less variability. All of the numbers, you're not going to get not like if you keep opening bags of M&Ms, you're going to get one with one of them in there. You're going to get less and less variable. It's going to start looking more and more like a normal curve. And so you have less variation between bag to bag. You'll start getting the same numbers repeated a lot more. And the numbers that get repeated the most are the ones that are closest to the average. or the center. And that's kind of what this slide is for here. It just kind of brings us to, I'm going to hit this begin button, but like, what it's saying is, let's say, maybe not M&Ms, goes from 0 to 32, maybe a small bag of M&Ms, I don't know. But let's say we take 5 small bags of M&Ms, right? So that's our first 5 bags right there. One of them had like, this is kind of a bigger disparity, but like one of them had like 8, 12, 14, and then maybe one with 20 and 22. Maybe in M&Ms, those are kind of really far away. But like the average of all those gives us that 1. So if I keep taking 5 more data points at a time, I'm increasing my sample by 1 every time. And so that's like my second average. These ones had a few more in there, right? And so if I keep doing this over and over and over and over again, these are more and more samples that I'm adding to my study, you can see that my data is going to get more and more normal. So this is only 5 at a time. What if I did 10,000 at a time? Well, it didn't animate them, but like if I did 10,000 bags of M&Ms, I get a very, very, very normal looking curve, right? So it's just saying like the average is probably this. This is what they want in each bag of M&Ms, but yeah, you do get some M&Ms that have a lot more and some that have a lot less. But on average, if you repeat the study over and over and over and over again, you will get a much more normal looking curve. And all of a sudden now your sample is so big that you can say, yeah, it actually does reflect the population, right? So your statistic that you get if you keep increasing samples is going to get closer and closer to the parameter, right? And that's kind of what the lesson is saying. So you guys can watch this video as many times as you want. Hopefully it makes sense, but certainly get those notes down. And then once you are all set with the video, you can grab that worksheet that you have. It's going to be called Sampling Distributions. Take care of that. You can hand it into the sub if you finish it. Otherwise, just do it for homework and I'll collect it next class. Thanks, guys.